Alright, let us solve this question. And finally we get our answer that is equal to 45 degrees. Wait, what? You're asking me how I found these auxiliary lines. Well, that is too easy a question for me to answer. But I do have an alternative way to solve this question. So first you need to establish a coordinate system, and then mark out the coordinates of the point. Do the same thing on the line segments involved in this question, and put them all into this formula, which basically turns this geometry question into an algebra question. Then solve for the unknown value and put the unknown value back into this formula. And quod erat demonstrandum. Welcome everyone to my math show. In this first video, I'm going to introduce a problem-solving method that I usually use to solve geometry questions. This method is called the vector method. I didn't see this anywhere on YouTube or Khan Academy. It's probably because you don't call this method this way, since I just use a direct translation from Chinese. So I'm not sure if you have heard of this, but if you have, you must have seen this formula. The angle between two line segments A and B is equal to the sum of the product of each element of their vector coordinates. Well, that's a lot of offs. And then divide all that by the length of A and the length of B. So that's the core formula of the vector method, and the vector method is about how to actually use this formula. So I'll just put it here. Okay, that's a core formula of the vector method. Let us switch to something that is more comprehensible, since you probably won't recognize that. And here is what it actually means. So this part is actually xb. So the shadow this line casts on the x-axis is xb, and the shadow A casts on x-axis is xa, and the angle between two line segments, theta. Actually, this thing is theta. The cosine, the angle between A and B is so cosine theta is equal to these things. And you may not realize that this is an extremely powerful formula and an extremely powerful method as well. When solving a geometry question, you can skip all the auxiliary lines and just find two line segments anywhere in the coordinate system, find their coordinates and calculate this, and you know their angle. So I have prepared a question here for you. So this question is made by me, and it's one of the few questions in two-dimensional geometry that cannot be instantaneously solved by the law of cosine. So I think it's pretty cool. You can try it out here yourself, but otherwise I'm going to prove this method. And if you don't care about proving, you can just skip to the solving of this question. But if you're some people like me who will never use a method or a formula unless it is proved, just stay here and I'll switch to the proving. Okay. So this is the first part of our proving. We have vector A and vector A prime. Let's assume they have the same length and the same direction. And by that, I mean vector A and vector A prime is the same vector. So I will write it here. Because a vector only has two elements. One is their length and one is their direction. So we can move a vector essentially anywhere in a coordinate system, and it will still be the same vector. So vector A prime is vector A with its start on the origin point, and then this point. This point has a coordinate x, y, and since its start is fixed, like if we draw any vector and we move it to here, their starting point will be fixed, and then each vector has a unique coordinate, which is basically a coordinate of a point that is called the vector coordinate. But let's go back to what we have here. I mentioned the vector coordinates of a line segment. So how does that exactly work? A line segment has a length, but it does not have a direction, or it can have two directions. One is towards this and one is towards this. So if we were to define a direction to this line segment to make it a vector, which way do we use? The answer is any is fine, because we are trying to figure out the angle between the two line segments, and if we turn them into vectors, we are trying to find the angle between two vectors. And then we will realize when I extend this, the angle between two line segments is not 1, not 2, but 4. So they are all angles between two line segments. So I find that it is pretty unnecessary to actually decide which way they are facing. Just calculate this YA and XA and you'll get the answer. Alright, you already know the vector coordinates, but it is still just a coordinate and you can't use it anywhere. But the vector coordinates actually have some real values, and I'll show you in a moment. Let's say if we have this vector and it is called vector XA, and then we have this vector and we call it vector YA. So vector XA has a length of x here. Vector YA has a length of y, and vector XA is towards the positive x direction. If x is negative, this vector is still towards the positive x direction, but it has a negative length, so it puts the vector towards this. But you can say it's towards the positive x direction with a negative length. It won't interfere with calculations. Then we can say the vector A is equal to vector XA plus vector YA. So a vector coordinate of xy means this vector can be expressed as a vector towards a positive x direction that has a length of x plus the vector that has a direction towards the positive y-axis and has a length of y. And now that's the first part of proving, just to let you know what is vector coordinates. And then we'll get into the dot product. This is also a familiar topic. As long as you know vector, you probably heard of this formula. So vector A dot vector B is equal to cosine the angle between them times the length of vector A and the length of vector B. This is how it is defined. Don't ask me why. So if we say that vector A has a vector coordinates of XA, YA, and vector B has a vector coordinates of XB, YB. So vector XA is a vector towards the positive x direction with a length of XA. and xa plus ya, and we still have the dot here. Xb is the same thing, plus yb. Alright, so luckily the dot product, the dot symbol satisfies the distributive law of multiplication. So that means we can deconstruct it further into this xa dot xb. They are all vectors, by the way, so far. And then we have xa yb. I'll write the vector symbol later. It's just faster this way. YAYB and vector symbol, vector symbol, vector symbol, vector symbol, vector symbol, vector symbol. And don't forget they all have dot inside. They are not simply multiplying each other, since you can't really do that in vectors. So here is what vector A dot vector B means. And this seems more complex, but as soon as we calculate their dot product value, you'll see why it is simpler, and you can see that it is basically our formula. So xa dot xb, they have the same direction, so the cosine 0 degrees is 1. 1 times the length of xa is xa, the length of xb is xb. There we go. And the xa dot yb, xa is toward the positive x direction and yb is toward the positive y direction. Their angle is 90 degrees, and cosine 90 degrees is 0, so I'll just write 0 here. And yxb, same thing, cosine 90 degrees is 0, plus 1 times ya yb, and you'll get xaxb and yayb. Now, if we move this here, if we move the length under this, since this thing is equal to this, and this is all the same thing, basically. So they are still in the same equation. Once we put their length under this side of equation, we will get the actual formula. Cosine the angle between vector A and vector B is equal to xa xb plus ya yb, and we have the length of A and the length of B in here. So that looks awfully familiar with what we had back here. ZAZB is optional. We don't need to consider that in two-dimensional coordinate system. And notice that I do not have the vector symbol on top of these things. So that may mean something. And let's go back to here. So the angle between two vectors can only be 1. They are not like the angle between two line segments. But when you are asking an angle between two line segments, you won't actually mind which angle it is. So I'll just erase this part, since you're looking for the angle, not one specific angle. And then we also have the vector symbol here. The length of vector A is actually the length of line segment A. So that's exactly what we had back there. But this thing is something that I came up with. It's not the official formula in the method. The official formula in the method has the vector symbol on top of A and B. But I think it's pretty unnecessary, since we have many things that doesn't really matter whether you use vector or not. And now let's get into actually this thing. Alright, so we have a square ABCD. And inside the square is a point P. Connect AP, BP, CP, and DP. We'll get angle APB that is equal to 90 degrees and angle PDC that is equal to 37 degrees, where cosine 37 degrees can be regarded as 4/5. And if the side length of this square is equal to 1, what is the length of PC? So this may seem like a clueless question, but once we have the angle, we can use our formula. But first, we are going to establish a coordinate system, as this is what we will have to do in every question that we will use vector method to solve. So here I'll set B as the origin point, as it looks simpler. Of course, you can set A, D, C, or P, or even P as the origin point of the coordinate system. Or you can even set this point. I don't know what it is, just O. You can even set this as the origin point, but I prefer not to do that, as it would make the calculation very hard. You can still solve it, but you will spend like 10 or 20 more minutes than I do. And then we'll need to mark the coordinates of every point. This is not necessary, but it can really help with the calculation. We'll use this often. And for point P, we do not know its coordinates, so I'll just say it has the coordinates of x and y. So we have the coordinates of 5 points. Now let's actually use the angles given. So what is our formula? The cosine AB is equal to, we'll need to put the vector coordinates of A and B there, and the length of A and B here. So let's back to the graph. Let's first see what angle APB can give us. So angle APB is the angle between AP and BP. And for vector coordinates, you only need to know the coordinates of the two ends. And you can take any of those two ends, take its coordinates and then minus it by the coordinates of another point. So you'll get x, y minus 1, or negative x, 1 minus y here. I'll use x minus 1 since I don't really want x and y to be negative here. And BP is, of course, x, y, or negative x, negative y. We also need to know their length, but actually in this case we do not. For the cosine angle APB is 0, and 0 equals whatever it is in the bottom, we don't care. So the upper part is sum of the product of each element of their vector coordinates. So that's x squared. So hard to write a square here. X squared plus y minus 1. So this is what we can get from angle APB. And you can see we only have one equation for two variables. We cannot solve this yet. So let's see what angle PDC can give us. So angle PDC is the angle between PD and CD. Let's say PD and CD goes here. I'll write them a little bit larger so that they are prettier. And then PD has a vector coordinates of x minus 1, y minus 1. And CD has the vector coordinates of 0, 1. The cosine 37 degrees is 4/5. 4/5 is equal to, on top of that, 0 times x minus 1 is 0, 1 times y minus 1 is 1 minus 1. And then down in the bottom, we have the product of their lengths. So the length of CD is 1. Since we are calculating for product, we can ignore that. And then we have the length of CD, which is quite long actually. x minus 1 square plus y minus 1 square. So now we have two equations with two variables. We can solve this pretty easily, or it is just possible. But for now, I'm going to solve the PDC equation first. Let's use a different color. 4, this thing, is equal to 5y minus 1. So what I'll do here is to multiply themselves on both sides of the equation, and we'll get 16 x minus 1 square plus 16 y minus 1 square. That is equal to 25 y minus 1 square. Then we can move the 16 to this side out, and we will get 9. So 25 minus 16 is 9. 9y minus 1 square. Square root both sides, and we have 4x minus 4 is equal to 3y minus 3. X is equal to 3y plus 1 over 4. And now we've completed the solving of angle PDC, and we still have one thing up here. So x squared is 16. 3y plus 1 square is equal to negative, actually let's have, is equal to y1 minus y. And then we will unfold this square to get 9y squared plus 6y plus 1 is equal to 16 to this side, 16y minus 16y squared. Then we put 16 here, we can get 25y squared. Put 16y in here, we can get 25y squared, and we get minus 10y, and then plus 1. This thing is equal to 0. And if you are aware of this thing is actually 5y minus 1 squared. Is equal to 0. This is 5y squared. This is 2 times 5y times negative 1. This is negative 1 squared. And then we have y is equal to 1/5. Y is solved, and x is equal to 3/5 plus 1, that is 8/5. 8/5 over 4 is 5, 8. We have 2/5. Okay, so we have x is equal to 2/5, and y is equal to 1/5. Now we have the coordinates of point P. So that means if we cast its shadow on x-axis, this part is 2/5, and this part is 1/5. That means this part is 3/5. It is 1 minus 2/5, that is 3/5. Okay, so the length of PC is pretty simple. PC is equal to 1/5 square plus 3/5 square. So that is equal to 5, and on top of that, square root 10. I don't think you can simplify it further. So that is the first question. I actually have another one that is three-dimensional. So we have this shape with a lot of right angles, and we have PA equals to AB equals to BC equals to AD over 2, that is equal to 1. So we can mark AD, that is 2, 1, 1, 1. It seems pretty simple, but what I ask of you is the cosine value of the angle between ABP and the angle between CDP. Normally, when you solve this kind of question, when you want to know the angle between two planes, you'll need to find the line they have in common, and then draw a line in each plane that is perpendicular to that line, and then calculate the angle between those two lines that are perpendicular to the line of the two planes in common. So that's pretty complex, but in this question they only intersect at a point. You'll need to extend this to get a line, and then you'll need to draw a line in each plane that is perpendicular to that line, and so on and so forth. So it is pretty arduous, and using vector method we can simplify that using a new concept, that is the normal vector of a plane. Here we have the planes alpha and beta, and here I'm going to introduce a new concept of finding the angle between two planes. That is, in this case, we are going to draw a line perpendicular to plane A and draw a line perpendicular to plane B. And now we get, let's just assume they are perpendicular, and extend this because they are lines. And then if we find the angle between these two planes and this one, they are not right angle, by the way, I'm just drawing it that way. We can see this thing, let's use light yellow. So we can see this thing is actually a quadrangle, and the angle between the two line segment, this angle, this one, is the supplementary angle of this one, since they have right angle here and here. So once we get the angle of the two lines that are perpendicular to the two planes, the real angle we want to know is 180 degrees minus that. That's it. Now let's get back to our real question. Again, if we want to use vector method, this is x, this is z, this is y. Again, you can choose any of these points as your origin point, but in this question is obviously A. Now you have AB pointing towards the positive x direction, and AD pointing towards the positive y direction, and AP towards the positive z direction. There's no point else as convenient as that. And now we mark out all the points. This is 0, 0, 0. B is 1, 0, 0. D is 0, 2, 0. C is 1, 1, 0. And P is 0, 0, 1. Let's say we have a vector E that is perpendicular to plane A, B, P. That's what we have down here. And we have vector F, again perpendicular to plane CDP. The angle between APB and CDP is 180 degrees minus the angle between vector E and vector F. And that means this whole thing is equal to negative cosine vector E and vector F. But what if the value we calculated, the angle between vector E and vector F, is an acute angle? An acute angle has a positive cosine value. With a negative before it, the cosine value of this will become negative, and the angle between two planes is an obtuse angle, and we don't want that. So this thing must be positive. So I will not use negative here. this is one thing that is kind of flawed in my getting rid of the vector symbol thing. If we maintain the vector symbol all the way through, we won't have to consider that. But I think finding the absolute value at the end of the calculation is way easier than being bothered by direction of vectors through the course of calculation. So I prefer this, and I'll just ignore the vector symbol everywhere. So let's say vector E has vector coordinates of xe, ye, ze, and vector F has xf, yf, zf. These are quite hard to calculate, but soon you'll find that you don't need to consider their length. So let's first get vector E solved. So vector E, that is perpendicular to plane ABP. So if a line is perpendicular to two intersecting lines in one plane, that line is perpendicular to this plane. So if vector E is perpendicular to AP and AB, the vector E will be perpendicular to the plane ABP. But in my opinion, we don't need to do that because we have AD already. So vector E can equal to AD or DA, anyway you want, and that has a vector coordinates of 0, 2, 0. So we don't even need to solve that. But for F, we need to consider if F is perpendicular to CD and DP at the same time. Of course, you can choose PC and CD or PC and PD, but I just think CD and DP has a rather simplified vector coordinate. So let's write down the PD, the vector coordinates of PD, and the vector coordinates of CD. The vector coordinates of PD can be expressed as 0 to -1. So I'm using D to subtract P. And CD is 1 minus 1. So vector F is perpendicular to PD. That means 0, which is cosine 90 degrees, is equal to, I'll ignore their lengths, doesn't really matter, they are perpendicular. And F, xf times, so this one is, by the way, PD, CD. Okay, so PD xf times 0 is 0, yf times 2 is 2 yf, zf times -1 is negative zf, and then come to CD. CD is 0 equals to xf minus yf plus 0. From the equation CD, we can get xf is equal to yf. And when we replace xf to here, we can find that we have 3 variables and only 2 equations. So f is impossible to solve. But again, does it really matter? Let's just give z a random value. Let's say zf is equal to 1. If zf is equal to 1, actually let's have it to be 2. If zf is 2, then yf is equal to xf is equal to 1. And then we can say f is equal to 1, 1, 2. And that might seem to be unreasonable since I just randomly gave zf a value. But I'll tell you that is perfectly fine, since if you give it a value of 4, it will just be 2 to 4. It's still pointing at the same direction, but it has a greater length. Length doesn't matter when we are trying to figure out the angle between vector E and vector F. So just randomly give zf a value. Remember to not give it 0, otherwise this would be 0, 0, 0. It would have a length of 0. which is impossible for a vector. But sometimes ZF is equal to 0, and if you find that ZF cannot equal to anything else other than 0, then ZF is equal to 0. So let us erase all of these and get into finding the angle between E and F. And this has become strangely easy since we have that formula, and we could just go directly to that. Cosine the value between E and F is equal to the length of E is obviously 2. The length of F, square root 1 square plus 1 square plus 2 square, that is square root 6. And then 0 times 1, 0, plus 2 times 1, 2, and 0 times 2, that is 0. So we can get rid of the 2, and this thing is equal to square root 6 over 6. And luckily, it is a positive value, so we don't need to change it. And that is the cosine value of that. And there goes our second question. Now it is the end of this episode. I hope you have enjoyed this video and hopefully learned something from it. The vector method has been an extremely useful method to me. Nowadays I solve almost every geometry questions using this method. So I guess that is my first episode. If you have any suggestions, please comment below. I love to see them, and see you in the next video.